Engineers often work with quantities that have both magnitude and direction. These quantities are mathematically modeled as vectors. Mathematics involving vectors is simplified by projecting the vectors onto a set of mutually perpendicular axes. Then the components of the vector can be analyzed independently. This decomposition is performed using trigonometric functions. This video provides an overview of vectors and the trigonometric functions used to analyze and model them. First, I'll talk about the difference between vector and scalar quantities. Some parameters that engineers work with are completely characterized by a number. These are called scalar quantities. An example of a scalar quantity is pressure. If I inflate a balloon, I increase the pressure inside the balloon. The pressure in the balloon doesn't really have a direction associated with it. The force caused by the pressure always acts outward from any point in the balloon. This means that we can express pressure purely as a number, like 35 psi or 35 pounds per square inch. Lots of times, however, a parameter will be directional and we need to account for that direction. These types of parameters are usually modeled as vectors. Force and velocity are typical examples of vector quantities. The force applied to this cart, for example, will dictate the direction the cart is moving. If I push the cart to the right, it'll move to the right. However, if I pull the cart to the left, it moves to the left. In order to model this behavior, we need to make sure we keep track of both the magnitude and the direction of the force applied to the cart and the magnitude and direction of the cart's motion. The trick to working with vectors mathematically is to define an appropriate coordinate system. A coordinate system simply provides a set of reference directions with which you can interpret the magnitudes and directions of your vectors. An example is the points of a compass. You can be going east, south, or southeast. Your direction of travel isn't dictated by the points of the compass, but it can be interpreted in terms of them. Keep in mind that there isn't a single correct coordinate system for any given problem. The choice of coordinate system for any problem is always up to the engineer. Use whatever makes sense for the problem you're working on. For example, in a city, directions of travel might be defined as uptown or downtown rather than relative to the points of a compass. Just make sure that your coordinates are consistent and that everyone who uses your results understands what coordinate system you're using. Although coordinate systems are arbitrary, some are simpler to use than others. Orthogonal coordinate systems are particularly convenient and are, in fact, nearly universal. In orthogonal coordinates, the reference directions are all perpendicular, or at right angles to one another. In more mathematical terms, they're said to be linearly independent, which means that they don't share any information in common with one another. In the example of compass points, north, south, east, and west are all perpendicular directions. This means that if you define an orthogonal coordinate system for your problem, you can represent any vector by its components in the coordinate system axes. Since the axes are independent, the analysis of each of these components can proceed independently. Next, I'll look at some orthogonal and non-orthogonal coordinate systems and how to represent vectors in orthogonal coordinates. One familiar example of an orthogonal coordinate system is a two-dimensional plot. We have a horizontal x-axis and a vertical y-axis. This is called a rectangular or Cartesian coordinate system. The axes are perpendicular to one another, and I can represent a point as a pair of xy values. However, just knowing the x value doesn't tell me anything about the y value. The two directions are independent. More specifically, independent axes mean that I can change the x value of a point without affecting the y value. Or I can change the y value independently of the x value. Let's contrast that behavior with a non-orthogonal coordinate system. These two axes are not perpendicular to one another. So if I move this point in the direction of one of the axes, I also get a change in the position along the other set of axes. Non-orthogonal coordinate systems can be convenient for some applications, but we won't be working with them. Another fairly common orthogonal coordinate system is polar coordinates. Polar coordinates are represented by a radial distance from the origin and an angle from some reference direction. I've shown rectangular coordinate systems here to provide a reference, but they aren't actually necessary. As with any set of independent axes, I can move a point in either direction independently. For example, I can change the distance of the point from the origin without changing the angle. Or I can change the angular position of the point without changing its distance from the origin. Finally, specifying a vector in a coordinate system requires us to represent the vector in terms of components in the coordinate system's directions. For convenience, these vector components are generally chosen as unit vectors, with one in each of the axis directions. For example, for a rectangular coordinate system, I'll specify unit vectors a hat x and a hat y. A hat x has a length of 1 and is purely in the x direction. A hat y also has a length of 1 and is purely in the direction of the y-axis. I can represent any vector as a sum of scaled unit vectors. For example, this vector A is 3 units long in the x direction and 2 units in the y direction. Mathematically, I can express this vector as 3 times a hat x plus 2 times a hat y. I'll go into this in more detail in the other videos in this chapter. For now, I want to move on and talk about how these basic concepts are used in engineering. Our example is to determine the acceleration of a block sliding on a surface. The block's acceleration has to be parallel to the surface the block is sliding on, but the force we're pushing the block with can be in any direction. The governing equation is Newton's second law, that the sum of the forces applied to the body is equal to the body's mass times its acceleration. There is another force acting on this body. That's the friction between the block and the surface it's sliding on. We'll model the friction with a friction coefficient b. The mathematical model associated with this type of friction is that the friction force equals the coefficient of friction times the perpendicular or normal force between the body and the surface. So the harder you push on the body downward, the harder it will be to slide the block. The friction force is always in the opposite direction to the body's motion, since it always causes the body to slow down. The solution approach I'll use to set up this problem is to project the vectors f, a, and f sub b onto a coordinate system of my choice. I'll pick a rectangular coordinate system shown in red here. The x-axis is in the same direction as acceleration and opposite to the direction of the friction force. The y-axis is in the same direction as the normal force between the block and the surface. I'll represent the applied force F in terms of components Fx and Fy in the x and y directions. Now, since the axes are independent, I can apply Newton's law independently in the x and y directions. If I sum the forces in the x direction, I get F sub x, since F sub x is in the positive x direction, minus F sub b, since F sub b is in the negative x direction, is equal to m times a, since its acceleration is in the positive x direction. Similarly, the sum of the forces in the y direction is negative F sub y, since F sub y is opposite to the positive y direction, plus F sub n equals mass times the acceleration due to gravity. The final piece of the puzzle is to determine the components Fx and Fy. We'll do that using trigonometry. Trigonometric functions are based on the lengths of the sides of a right triangle. If I have a right triangle that has sides with lengths A, B, and C, B is equal to C, the hypotenuse, times the cosine of this angle theta. Likewise, A is equal to C times the sine of the angle theta. The math is the same for vectors. If this is the vector F at an angle of theta to the x-axis, the component in the x direction, F sub x, will be F times the cosine of theta. The y component of the force, Fy, is F times the sine of the angle theta. Those are the basic pieces necessary to do an engineering analysis with vectors. I'll do more examples and add details in later videos, but the main steps are to choose an orthogonal coordinate system for your problem decompose the vectors into components in the directions of those coordinate axes, and then apply the governing equations independently in the different coordinate directions.